Good afternoon to everybody. The title of the seminar today is Charge Transfer Complexes, Implementation in Solution Processed Organic Field Effect Transistors. And the speaker is Maria Elisabetta Giglio. She got her master's degree in physics at University of Heidelberg in Germany and developed her thesis in the Karus Institute Technology, working on the development and the optimization of the production process of thin films characterized by the uniaxial alignment of a high-mobility organic semiconductor polymer named DPP-DTT. During her time in Germany, she has also deepened her knowledge in the fabrication and characterization of organic electronic devices by working as an employed assistant research science for the same institute, as well as for the Technische Universität Darmstadt. Now she is a PhD student at the Institute of Material Science of Barcelona within the EMOLMAT group of Marta Mastorrent of the Department of Molecular Nanoscience and Organic Materials. Her doctoral project acts in the field of molecular electronics with the aim of producing electronic devices as organic field effect transistors based on organic semiconductor thin film prepared by printing methods, as well as studying the transport properties of organic molecules to better understand the transport mechanism at molecular level. So, Elisabetta, thank you for accepting my invitation today. You can share the screen when you are ready, and you can start. The floor is yours.
Thanks to you, Sara. Thank you very much for the presentation. So I'm going to share the screen now. Can you see that?
Yes.
Amazing. So thank you very much for being here today. I will talk about our current project in the group here at ICMAB. This is about charge transfer complexes and their implementation in solution processed organic field effect transistors. So I will give you now an introduction about organic electronics, because organic electronics is a research field in an expansion that is focused on the design and the synthesis of new organic molecules primarily, and then the application and the characterization of these materials in electronic devices. So electronic devices, what we are talking about. Mainly, we can divide the organic electronic devices in three domains. The first one is organic solar cells. The second one is organic light emitting diodes, or OLEDs. And the third one, but not less important, organic field effect transistors. So why organic electronics? Because in organic electronics, we can exploit organic molecules in order to fabricate lightweight devices that can be also flexible and wearable. The fabrication processes are low cost, and we can also fabricate like stretchable devices. And very important, we can process the materials by solutions. And I mean, all these devices are in general compatible with plastics, which is not, all these are not features that are afforded with inorganic semiconductors that are like all in the modern electronics, which is silicon based. So I am going to introduce some key concepts, that is organic semiconductors and charge transfer complexes. And first of all, I will talk about what are organic field effect transistors, and I will introduce the concept of solution processing to you and show some results as well. So let's start from the definition of organic field effect transistors. An organic field effect transistors is a three-terminal device where the current basically flows between a source and a drain electrode, and is controlled by a third electron that is the gate, as you can see in the diagram here. So basically, we have the three electrodes. Source and drain are, in our case, evaporated, so they are gold electrodes. And then we have the substrate, which in our case is silicon and silicon dioxide, which is the dielectric. and the gate is represented by the silicon. Then the active layer of the transistor is represented by organic semiconductors as thin films. So depending on the active material that we use in the transistor, we can basically obtain two different behaviors based on the nature of the charge carriers in the active materials that can be N-type and P-type, depending on the nature. So for the case of N-type, we have electron transport, and for the case of P-type, we have holes. So I will take as an example a P-type organic semiconductors where the charge carriers are holes, and I will explain the working principle of an OFET. So first of all, if we don't apply any voltage to the electrodes, we have a situation where basically the device is off, but if we apply a voltage between the source and the gate, we are creating a conduction channel in the active layers, and in this way, the charge carriers are available for the conduction. Then, when we apply a voltage between the drain and the source, we create a current between the source and the drain. So, for the P-type configuration, the voltage that we applied are negatives. So what we do with transistor is like electrical characterization in order to study the performances of the devices, and we mainly carry out two types of electrical measurements. The first one is the output characteristics, where basically the voltage between the source and the drain sweeps at constant source gate voltage, and then we measure the current between the drain and the source. The second one is the transfer, where the voltage between this time source and gain sweeps at constant voltage, say source drain. Looking at the output, we can distinguish between two operation regimes. The first one is a linear regime, which is basically on the right side here in the plot, and the saturation regime. Talking about the transfer, well, this is very important because we can basically calculate a lot of parameters that are of interest. Talking about the performances. So the first one is the mobility. So basically we calculate the mobility by making the square root of the absolute value of the drain source current, and then we make like a linear fit of the current as defined like this, and by calculating the slope, then we can extract the mobility, the field effect mobility. Then also another very important parameter is the threshold voltage that ideally should be very close to zero. Then we calculate from the drain source current the speed with which the transistor is turning on, which is called like subthreshold slope basically. And then what we want to see is the maximum value of the current and the ratio between the on state and the off state in terms of current. So in order to obtain high-performing organic field effect transistors, then we have to obtain high mobilities. The threshold voltage needs to be low, ideally close to zero. And we want a low subthreshold swing, which means that the device has to be very fast in turning on. We want a low contact resistance, so between the electrodes and the active layers. They have to be stable under air atmosphere as well as under bias stress. There are a lot of applications when we talk about organic field effect transistor that, I mean, they can go from sensors to organic light emitting transistor, artificial synapses, or memory devices, but also much more. So now I gave you an introduction on organic field effect transistor, and I will talk about what are organic semiconductors, and specifically what are charge transfer complexes. So organic semiconductors are mainly conjugated small molecules or polymers that form supramolecular structures based on pi-pi interactions of their molecular orbitals. So in the first case about polymers, they have like very big structures. However, when they form like crystalline films or amorphous films, they are affected by structural disorder. However, they are very, the solubility is really good, and also the viscosity is really high, and this is very nice when we think about processing, because we want to process all these kind of materials by solution. And then on the other side, we have small molecules that we are particularly interested in our group, that are very high structural order, they crystallize very well. However, the majority of them is affected by a low solubility or low viscosity. So the first generation of small molecules, organic semiconductors, is represented by pentacene. So pentacene, for example, have a very high level of structural order. However, it's low soluble and it's low viscous in solution. And then the second generation of this kind of molecules is represented by TIPS pentacene, which basically have the same properties of high structural order, but in addition have a very good solubility due to the new functional groups that have been added to the pentacene structure. However, it's still low viscous in solution. And then the third generation of this kind of materials is represented by the blending of, for example, TIPS pentacene with polymers such as polystyrene, which adds basically the good viscosity in solution. Moreover, we have also other kind of molecules that can be added in this case, to TIPS pentacene, that is a p-type organic semiconductors, can be added as dopants. So we have another class of small molecules that are also n-type, like F40CNQ, for example. But then, so I'm talking a lot about organic semiconductors, but what are charge transfer complexes? That is like the topic of today. So basically, a charge transfer complex that I will call CTC is a binary system composed of a donor, which is a p-type organic semiconductor, and an acceptor, which is an n-type organic semiconductor. And basically, what happens in the binary system is that the electronic coupling between the highest organic molecular orbitals of the donor and the lowest unoccupied molecular orbital of the acceptor occurs. And so this basically leads to the creation of a new energy band of the new complex, with a resulting degree of charge transfer between the HOMO of the donor and the LUMO of the acceptor, leading to a ground state with partial ionicity. The degree of charge transfer is very interesting because it defines the electrical properties of the final complex, and it can be modulated by different ways. One way is like by tuning the difference between the HOMO of the donor and the LUMO of the acceptor. And another way also is by acting on the supramolecular organization of the final complex, which defines in the end the bandwidth of the final complex. So based on these, the charge transfer complexes can show very different properties entirely with respect to the parent compounds, which usually are unipolar semiconductors. So basically, thinking about this, we can, a lot of properties have been detected so far in literature, and these properties can vary on a wide range from insulators to semiconductors to even conductors as superconductors. And moreover, other properties have been seen, such as photoluminescence, photoconductivity, which is very interesting for us, magnetoconductance, thermoelectric properties, and ambipolarity. So basically, charge transfer complexes can be seen as an approach to tune organic semiconductor properties, which are usually unipolar semiconductors. So, what about the crystallization of these charge transfer complexes? Because when we think about a transistor and small molecules, we want to have crystalline films. So basically, the charge transfer complexes can crystallize into different configurations. One is the mixed stack configuration, and the other one is the segregated stack, and it occurs by co-assembling of the donor and the acceptor molecule. And what is interesting is that the performance of transistor based on these single crystals are comparable to the ones of the amorphous silicon-based transistors. So, for example, among a variety of organic semiconducting materials, single crystals have record charge carrier mobilities that are really high. The rubrine is an example. We reached field effect mobilities of 15. And as I told you, by tuning the degree of charge transfer, we can tune the conductivity of the material and also the properties, but also the supramolecular structure has an impact on this. And we can see in this graph that there is a clear separation between, in terms of conductivity, between the segregated stack configuration and the mixed stack. So, charge transfer complexes has been widely studied in literature, but mostly as single crystals produced by drop casting techniques, co-sublimation of the parent compounds, or co-evaporation. But what about CTCs in transistors? So the literature trend is see them used as single crystals produced by co-evaporation or drop casting, as well as thin films fabricated by co-sublimation. When we think about CTCs, basically we have to take into account the low solubility of the donor acceptor mixtures, and the processing of the organic semiconductor layer is a fundamental step in order to achieve high quality devices and in order to overcome all these issues about solubility. So basically, the use of single crystals is almost as no use in practical applications, but thin films, yes, they have, because there are many potential applications when we think about thin films. Why? Because techniques such as drop casting, spin coating, or co-sublimation are techniques that can be done only at laboratory scale. However, industry is demanding processing techniques that are compatible with real application and specifically with roll-to-roll methodologies. So we are thinking about printable electronics that has to be also scalable and compatible with large area. So the challenge about solution processed organic semiconductors is that we have the best mobilities in single crystals devices and processed by films processed by vacuum deposition. However, there is a balance between, we have to encounter a balance between performances of the performances of the single crystals that are fabricated with laboratory techniques and the processing demanded by industry. So we want processing techniques that are low cost, large area compatible, solution based, and techniques where we can optimize the coating condition. In our group, basically we want to overcome the solubility issues about CTCs, And we want to employ a solution processing techniques called Bar Assisted Meniscus Shearing. That is a technique that we developed in our group. The strategy when we use this technique is that we want to produce films from a solution. So basically we have to prepare the inks, and the addition of the polystyrene as an insulating polymer is key in order to enhance the processability of the materials and to also obtain high mobility and a high crystallinity of the material. So first of all, we position the substrate on this platform, and we inject the ink, so the solutions previously prepared with the materials, in between the substrate and the steel bar. After that, we move. We start the movement of the platform, which basically, well, there is. Okay, here there was a video that is not showing up. Okay, doesn't matter. Okay, so basically by the movement of the platform, basically we drive the crystallization of the film, because when we inject the ink, we create a meniscus, and then the meniscus drives the crystallization. So in the end, we obtain highly crystalline films and very homogeneous. So the advantages of this technique is that it's very fast. We can process the films at 10 millimeters per second or even more. It produces very crystalline films. It's compatible with plastics, compatible with flexible. It's compatible with the roll-to-roll mentioned before, and can be scalable. The role of polystyrene, however, is not only about the processability of the inks, but also it plays a fundamental role in the vertical phase separation of the materials. Indeed, we discovered that basically when we add polystyrene in solution with the semiconductors, when we deposit the films, there is a vertical phase separation between polystyrene and the semiconductor. And this is very important because basically the layer polystyrene passivates all the charge traps at the interface of the semiconductors and the dielectric. And this is very important in order to enhance the performances of the final device. So basically, I'm going to make a resume here. So we prepare the inks with the materials, so mainly the semiconductors of our interest and the polystyrene. Then we fabricate the films by the Bar Assisted Meniscus Shearing technique. And then, very important, we study the morphology and the structure of the films, of the active layer. And then we perform all the electrical characterization of the final devices, studying the response. So the morphological studies are very important, and we perform a lot of different techniques, such as polarized optical microscopy, atomic force microscopy, X-rays diffraction, infrared spectroscopy, Raman spectroscopy, and more. So why morphology is so important? Morphology is so important because a lot of parameters, a lot of features of the morphologies have a huge impact on the final performance of the transistor. So when we think about the film, we have to think about the crystallinity of the film, so the orientation of the crystals, the crystal size, the density of the grain boundaries, the coverage of the crystals, and as well as the thickness, the roughness. Sorry, here there is a repetition. And all these parameters can be basically tuned by optimizing the coating parameters that are mainly the speed, the temperature, but also the ink formulation. So basically, here going more deeper into the methodologies, we use polarized optical microscopy and atomic force microscopy in order to study the morphology, the coverage, the homogeneity of the films, as well as the thickness and the roughness. Then we perform X-ray diffraction that works, of course, only with crystalline films in order to define the molecular structure of the crystals, the orientation, the phase, as well as the polymorphism, which is like all the ways that the crystals can form with, basically. So talking about CTCs, so charge transfer complexes, we know that the bond lengths of the molecules are known to change as a function of the degree of charge transfer. So this is also like a first method in order to detect the presence of the charge transfer as crystals. Then we perform infrared spectroscopy as well as Raman spectroscopy, which are fundamental techniques in order to determine the vibrational modes, as well as to study and identify the functional groups of the molecules, the chemical footprint of the molecules. And talking about CTCs, we basically exploit the dependence of some specific stretching frequencies and as well as oscillator strength of the charge transfer band on the moiety charge. So basically, we can calculate the degree of ionicity, so the degree of charge transfer between the donor and the acceptor, by the calculation of the frequency shift of some charge-sensitive vibration in infrared spectroscopy as well as in Raman. And then we can also calculate the optical band gap from the onset of the charge transfer exciton absorption band. So in our work I want to present here, we basically used the phenyl BTBT C10 as a donor and the F40CNQ as an acceptor, blended with the polystyrene in solution. And we use a mixture of two different solvents, that is chlorobenzene and benzonitrile, because the BTBT is very soluble in chlorobenzene, but the F40CNQ is not very soluble in the same solvent. So we add benzonitrile, that is a solvent where we can easily dissolve the F40CNQ. So basically what we do here is, well, we try different methods. One is the ones that you see in the video, which is mechanochemistry. So we mix the two materials as powders and then we dissolve them. And we perform also ultraviolet visible spectroscopy in order to see light changes in the peaks. And then we can see also a change in the color of the solution when the donor and the acceptor are interacting and forming a charge transfer, because basically the solution turns to black. So it's clearly visible and it's very nice to see it. So about the fabrication, well, we do a lot of several things, because we start from zero basically. So we fabricate bottom gate, bottom contact transistors. So what we do is photolithography in order to expose the silicon wafer to the pattern that we want. And then the technician perform thermal evaporation of the electrodes, which are basically 5 nanometers of chromo and 40 nanometers of gold. And then we activate the gold by plasma, basically oxygen plasma, and deposit a self-assembled monolayer of PFBT on the electrodes in order to align better the work function of the gold with the, let's say, work function of the material. So after that, basically, we can deposit the film by the techniques, the bumps. And then in the end, we got a very homogeneous film, crystalline, of charge transfer complexes. We perform X-rays diffraction, and we could see that there is a very good agreement between the experimental results of the film with the simulation of the single crystal, as well as the measurement of the single crystals. And then we also perform, this is done by a collaborator of mine, Dr. Tommaso Salsillo in Bologna. So they performed the Raman spectroscopy and infrared, and they confirmed the presence of the charge transfer complex in the film. And then in the end, by performing the electrical characterization, we could see that we got basically N-type transistors. So in the end, we have an N-type that actually is not very stable, but and also the mobility is not really high because it's of the order of 10 to minus 3. But the interesting thing here is that by performing photothermal deflection spectroscopy, which is a very high sensitive technique, we can see a very nice peak in the absorbance in the infrared region. So as I told you before, when a charge transfer complex is created, there is like a deformation of a new band gap that is narrower with respect to the one of the parent compound. So basically we have a redshift in the absorbance spectrum. And in this case, we are exactly in the region of the infrared, which is very interesting because we can think about the use of this transistor as photodetectors. So for sensing applications, basically. So we are currently working on the optimization of these phototransistors. That, well, thinking about real applications, we can think about oximetry, for example, so the detection of oxygen in the blood, so medical applications. And this is all for now. So thank you very much for your attention. And I want to thank also all my collaborators and my group IMOLMAT. Thank you very much.
Thank you, Elisabetta, for your very nice and interesting presentation. So now it's time for questions. You can ask, or maybe you can write in the chat and then I can read them for you. Well, in the meantime, okay, we have a question. We have a question from Dan. Great talk, thank you. Can you predict which types of molecules will interact to form charge transfer complexes?
Well, nice question. Thank you very much, Dan. So predictions, well, somehow yes, because we have to think about like the donor acceptor molecules. So for example, if we take in our case F4 TCNQ, so I go here. For example, in the molecule we can see that there are like 4 fluoros, so which is a very which has a very electro affinity, a very high electron affinity. So we can kind of predict the degree of the power of let's say electron affinity of the final molecule. So this is a very good acceptor for electrons. And also, if you think about BTBT, it's the same thing basically. So it is very important. So because we work together with chemists in order to synthesize also molecules that has this kind of behavior of donor and acceptor. So we can kind of predict. In the end, it's difficult to predict the behavior of the final devices. So this is difficult, but the creation of charge transfer, yes, because actually it's really common also in doping, the creation of charge transfer. So yeah, I don't know if I answered the question.
Probably yes. Thank you. Yes. More questions, curiosities? Don't be shy. Well, in the meantime, I have just a curiosity. You talked a bit about the real application of these systems, but which are the costs? Are there some systems that are already commercial at the moment? And in general, I mean, how challenging is the practical organization of some system like this?
Well, it's really challenging because even if the material absorbs in infrared, we have to think about also the amplification of the photocurrent, which is not so easy. So we are actually working on that. About the cost, well, I don't know actually if about the actual cost. I mean, now we are exploring this kind of devices, and I mean, of course, the materials are not so cheap. Also, we are using silicon steel, but because it is like a standard platform in order to study the materials themselves. So I don't know. This is a thing that we have to study a bit.
But in the end, as you told, are versatile systems, so probably it's possible to optimize and.
Of course, it is. I mean, the ideal case would be like also to fabricate flexible devices. So by substituting the silicon and the silicon dioxide with flexible, so with plastics. So yeah, this will be like the following step.
Okay. And just the last curiosity, maybe I lost this information a bit. Why organic transistor is better than other one? You told something about advantages, but if you can
Okay.
like explain me better, yeah.
Okay. So here.
Yeah.
So they are better, well, better, I would say. They are quite different because, I mean, the silicon is like a very rigid, has a very rigid structure. However, they are very high performing, no, in devices. So the challenge of organic electronics is to like reach the same kind, or at least try to reach the same kind of performances, which is very difficult. But they have advantages that the silicon doesn't have, which are like the materials in the organic materials can be solution processed. So this means that you can use a lot of fabrication techniques that involves the use of inks, so use of solutions that are low cost and fast. Then you can fabricate flexible devices. So basically you can use plastics with organic materials, and also you can fabricate very light devices. I mean, silicon is doesn't have all these features. So yeah, I mean, we can also, another advantage is that chemists can synthesize a wide variety of molecules that we can test. So I mean, it's a very open field at the moment.
Yeah. So maybe the key point is the versatility at the end.
The versatility, yeah. Also, the key point is that you can process the materials in solution. Yeah.
Okay, fine. Thank you. So, are there more questions? See. So, if not, thank you again, Elisabetta, for
Thank you very much
today for your presentation. And well, we can move on. Well, just a bit of information about next Thursday. Next Thursday, we will have a physics seminar about flexoelectricity in two-dimensional materials. So that's all for now. See you next Thursday.
Thank you very much. Bye-bye.
Bye.
Bye.
Yeah, bye-bye.
Very interesting.